Okay, thanks. Thanks for having me here. Just like Joe, I am also an industrial engineer working for Boeing for 35 years. I just had my anniversary. So I have seen many things in the past, being an IE, writing things down by hand, doing time studies, to today's world, which everything is digital. So I'll be talking about our infrastructure at Boeing, and then I go into some use cases. I have about 10 use cases. I'll go through them quickly and explain what they are. Okay, so most of you know Boeing is a large company, aerospace manufacturer, is known for commercial products, but we also build military products. That's the division I am from, actually from St. Louis, Missouri, where we build fighter jets. But two of the products that I'm showing you, those are both wide-body airplanes. 787, which is an all-composite structure, fuselage and wing both. That was first introduced as one of the largest airplanes that's fully composite material. And what it does is that the material results in 20% weight reduction and the equal amount in fuel efficiency. So with that in mind, we had the 777 product, which has been in the market for a number of years, maybe 10 years, 200 and 300 ER. Now, last month, we had the rollout for 777-9. And the difference in this product is that the wingspan is all composite, and the wing is so large, 72 meter, that we have a folding wing to fit inside the airport terminals. Okay? Again, it's for fuel efficiency and modern infrastructure with electronics. Okay? When it comes down to data collections for the factory, I heard about MES. We do have MES, we have ERP. That's been done many years ago, but our challenge is how we connect these systems together. You know, at the low level where we have a machine running, how do we pass the data up and compare it to the schedule that comes out of MES? So this is very complex, and for Boeing, we need large systems. So I started doing this like 10 years ago on my own. Basically, they gave me a budget from a research organization. Said, okay, go and work on it, show us some examples. So what I did was to introduce pilots in the factory. And we had our own data collectors. We built our own system and infrastructure, including communication, data analytics, and visualization, basically. But now I have grown this into the enterprise, because using my experience for what I've done in the past is I'm working with the IT organization to bring standards that make sense for large-scale deployment. Okay? So there are three types of data that we are concerned about when it comes to machinery. On the left-hand side, we have the basic data, basically overall equipment effectiveness for the machines. We like to have this on every piece of machine. And that is availability of the machine, performance of the machine, and quality that comes out of the machine. So these attributes come out, and we have to calculate. There's a formula behind it. You can look it up about OEE, how to do that. But it's digitized within our equipment and process. Most of the data comes from the machine control. Very few cases we have to add our own sensor data. In the middle box there is a process control. So when it comes to assembly and basically final assembly, we have to have customized equipment. So we order the equipment to build a product. So what is important is to have the product compare, as far as quality, to the design. And that's where the digital twin concept comes in. So we can look at the physical product and the design, and the data is the difference between the two, and how we can minimize that to have a perfect quality product. And on the right-hand side, our maintenance department is always concerned about health of the equipment, how to keep it up, keep it running all the time. So we look at data such as mean time before failure, mean time to repair. We look at the work orders, the history that comes into the back-end systems, and from that we do analytics to see what the recurring problems with each equipment and what actions we need to take. Okay. I work with Georgia Tech, as I borrowed some of the slides from them. We have some bright students working there. They are in their mechanical engineering department. They have like 150 pieces of machines. And students go and sign up, and they can work with the machine. But what I encourage them to do, and what I propose for also Boeing, the systems that we are using, is to use standard methods like OPC UA, we.CONECT, and that's what we use. We use them at school, we use them at Boeing. And then all of this is rolled up to tools that we have, like MQTT messaging protocol and JSON messaging service. At the top, you see our legacy system. The system has to be connected to the business process in order to make sense. Okay. I also work with the National Institute of Standards Technology and ASME. And within that, we understand that, well, yeah, Boeing is a large company, but what do we do when you have a machine shop with 5 machines? You can't automate everything. There is no ROI. So there are different solutions for different conditions. So within the guidelines, we categorize the type of need, whether the need is for planned maintenance, reactive maintenance, or condition-based. And then the decision can be made from that to know, well, you need a full automation in our factory, or you could do maybe a periodic or planned maintenance and be okay. So it comes down to return on investment. And one thing from this chart that I'd like to suggest is that we shouldn't tie ourselves to equipment lockout with proprietary information coming from the supplier, because we kind of lock ourselves into working with them the whole life of the equipment. So it's important when we write the spec for the equipment to make sure that we have data and it's compatible. Again, we.CONECT, OPC. It's good to ask for health-ready equipment so we have less trouble and cost at a later time. So the rest of my presentation is all about use cases. So I'd like to kind of show examples, and you can ask questions afterwards. So for the composite structures, we have laminating machines. These are automated machines that lay fiber tows. What you see, the 2 pictures there, is a barrel of the 787 airplane. So it's toward the tail end of it, section 47 and 48. So we wind composite material. The toe is only 1/4 inch wide. And we wind around the barrel. The challenge is that if there's a gap or overlap between the material, that causes rejections. So the older technology, when this program started, was to stop the machine and visually inspect, any gaps and laps. So you have to have really instrumented eyes to do that. But we roll the barrel and check for that. New technology is that we have camera systems that constantly work with the machine head, with the end effector, and they look for it. And after each layer is put down, the machine goes into the inspection mode, and we do that to find out if there is a problem. Okay, over at the metal fabrications, and we have 2 large facilities over at Auburn, Washington, and Frederickson, Washington. So in this area, we have quite a few machines of same kind. Like we have Mazak machines, maybe 40 of them in one area. So what is kind of easier to do is to compare the machine performance and look at the data and degradation from each one. And we'll be able to tell if there is a a problem with one of the machines if the data tells us that there are differences. And the older machine, the challenge is that none of them are instrumented. So we have to add an industrial computer, edge device that was mentioned earlier to be able to collect the data. And what is important is to understand what kind of data is important, because we have to invest in order to have the data. So that kind of analysis is important for industrial engineers, manufacturing engineers, process engineers to recommend what to do for this type of machine. Over at the assembly areas, I have two examples here. On the right-hand side, I have the gem core machines. There's like 7 of them for 777. And they drill holes and install a rivet in 20 seconds. And there's about 20,000 holes for that skin that you see in the picture. So what is important is the speed of operation and lack of failure. So that's what we look for that type of equipment. On the left-hand side is the FA-18 drilling system. So for that, we drill 1 hole every 3 minutes. Why? Because we have 2 inches of materials, titanium, composite, aluminum, and we have to go through all of that, and it has to be done at a slow speed because the tolerance is plus or minus 0.005 of an inch. So depending on the use case, we have to look at what is important, what kind of quality data we need to collect to be successful in making good holes. In the southern states, we have heating and cooling systems because the buildings have to be air conditioned. You know, we can't have uncomfortable environment for our workforce. So we have HVAC systems on the roof of the building. So how do we know if the system is working correctly or not? And you know, we can't wire up the HVAC, you know, motor that's maybe a few $100s. It may not make business sense. So we introduced wireless sensors and temporary monitoring systems to have sensors that we put on a system, and then we might take it out, you know. But it would tell us, you know, quickly to a tablet PC that if the vibration is the same, if there are problems that we need to look at. Okay. Freezer monitoring. So I mentioned composite many times. So composite shelf life is 12 months inside the freezer, but if the materials is taken out of the freezer, it's 30 days or less. So it's important that we monitor the shelf life of the equipment until the material is cured. So there's software pieces to do this. We have RFID equipment at the entrance and exit of the freezer. That's how we know when the material comes in, it has like 300 days left, you know. And if the material comes out with low shelf life, we have to put priority on it to go to the autoclave faster. So that kind of monitoring system is important in this case. Clean room monitoring. So we have to stay within compliance for the clean room. The temperature has to be 70 to 75 degrees Fahrenheit, and humidity about 40%. So we have data collectors that we place inside the clean room, and these are large areas, like a couple of 100,000 square feet. And the collectors are in different locations because you can't just average them out. You know, there might be a sanding process next to a sanding room, and the door opens, and so we need to know if that causes problem, you know, with compliance in the whole room. So these are scattered around, but they're tied to the network. So what I've copied under there is information coming out, so we can look at the temperature and humidity. And I'm tied to this. You know, a lot of times the power goes out and I get email, you know, that there's a problem in the clean room. And oftentimes I send a message, but most people know because there's more than me tied to the network. And for situational awareness, we have passive and active RFID systems. So the passive system, just like Walmart and other retail stores, at the entrance to the doorways and the dock areas, we have passive RFID. So boxes of material that come in, we can monitor them and understand, basically when they come in and the location of the part, okay? And for active RFID, these are higher price sensors that we put on valuable assets. So when parts move, we might have a sensor attached to it. And we have locators inside the factory that they can triangulate and find the asset within a few feet. So if you can think about how many assets we have, it's a complex problem, and losing parts is an issue. So RFID comes to help. We have it deployed in most of our plant, at least the passive part of it. And I have a couple of other safety projects that I'm working on. This one is about AGVs. So guided vehicle move inside the factory, but I can tell you that even now within Boeing, we have to have a person walking behind it because we don't trust AGVs running by themselves. When they carry 40,000 pounds of material and they have to drive all the way from clean room to the autoclave, well, what if they run into a wall? So, we don't trust that. But what I have here in this pilot project, in one of the sites, we have cameras all the way along the path. So the cameras report the situation of the vehicle to the vehicle control management. So if I have an example that, you see two people standing there. We did that as a test. So they're standing on the AGV path, and you want the AGV to stop and see how quickly cameras can report the status. And this is, again, in pilot mode, but it's working. It's working well, and we like to try to expand that to other sites. And for confined space, the airplane has areas that are confined, like inside the fuel tank. We have mechanics that must go there and seal the areas. We have inside the wing structures like a fuel tank too. So all the holes have to be sealed, okay? So this is a difficult process that if somebody crawls in, some of the wings are big, but others might be smaller. I can't imagine sometimes how big people go in there, but they have to work in that environment. So, and when they go inside the confined space, nobody can see them. So we require that each person will carry a radio, okay? And there's a control station that monitors all the entrance to the confined space. And this year, we're planning to add a gas detector as well. Okay, gas detection is done periodically today, so we have runners going every hour, and they check the air quality in confined space, because again, working with sealant and other chemicals. But the idea here is to have both devices, communication with voice and gas detectors, to be able to know, situation awareness about the workers. Okay, and lastly, this is my last slide. This project is about paint stackers. We had painters that work with stacking platforms. We have all the time, but the situation was that we had an accident that a person who was actually thought that he was hooked up to the lifeline walked off the platform, and caused injury. So I was asked to help with this project, and what we did was to create an interlock system so that the harness is attached to the SRL lifeline, and if they're disconnected, we send a message to the PLC not to move, so the platform will just stall, and this prevents, accidents like what we had before. So with that, I think that's about all I have, and I'm happy to answer any questions.